Alright, so here's the next screencast for Honors Chem on identifying reaction types. So our essential question is, what are the basic differences between each of the different reaction types? So instead of just being able to balance a chemical equation, we're now going to look at chemical equations and be able to tell what type they are. So this is kind of the basic formatting for this. We're going to go through synthesis, decomp, single replacement, double replacement, and combustion reactions. And if you look, I've provided you with a example or kind of a simple skeletal structure of what these compounds look like, or what these reactions look like. So a synthesis reaction, it's also known as a combination. You're taking things and you're putting them together, so you're only going to have one product. In a decomposition reaction, you start with one reactant and you break it down. So these two are opposites of each other. In a single replacement reaction, you can see that you have one element, Y, taking the place of another element in the compound. So like Y kicks Z out, and so ZY now form a compound, or X gets kicked out in this case. Y could kick out Z, Y could kick out X, depending upon if it's a metal or a non-metal. In a double replacement reaction, you'll notice we have a compound, and then we form two new compounds. So they just switch partners with each other. And then in a combustion reaction, you start with some hydrocarbon and you react it with oxygen, and you're going to burn it to create carbon dioxide and water. So those are the reaction types we're going to talk about. So our first one is synthesis or combination reactions. Our kind of basic reaction is just X plus Y equals the compound XY. So you can always identify these because you're going to have reactants in the products, and then, or on the reactants are going to be elements, and then the products are going to be compounds. There may be more than one reactant. Most of the time there's going to be more than one reactant, but there will always be only one product in these reactions. So here's some examples. Iron rusting. Iron reacting with oxygen in the air to form iron oxide. So you see that I have two elements combining together to form one compound. Water rockets, the water rockets that we did. Hydrogen gas combining with oxygen gas to form water. Magnesium burning, magnesium plus oxygen gives you magnesium oxide. You'll notice what makes these synthesis reactions is you just have one product. Decomposition reactions are the exact opposite. You start with one reactant and you have multiple products. So your reactant is always going to be a compound, and then you end up with multiple products, which are either going to be elements or compounds. These reactions often involve heat, light, or electricity, as you need something to like spark the reaction happening. They don't just spontaneously happen on their own. Things don't decompose generally on their own. They need something to get them started. And here are some examples. Electrolysis of water. You use electricity to separate hydrogen and oxygen into hydrogen gas and oxygen gas. Hydrogen peroxide, you can get that to break down into water and oxygen. Baking soda, you can take the sodium bicarbonate or sodium hydrogen carbonate and you can get it to break down into sodium carbonate, water, and carbon dioxide. So even though there's three products in that third one, there's still only one reactant. So the way you can tell these reactions is there's only going to be one reactant listed. Single replacement or displacement reactions happen when one thing takes the place of another thing. That's why it's called a single replacement. Generally, you have a compound and an element, and in the products you form a new compound and a new element. So you can identify them pretty easily by just seeing compound element, compound element. One element replaces a second element, and they're going to form a compound. You generally see this with ionic compounds. And you have to have a reactivity series to be able to tell if these reactions are going to go. When we learn how to predict products, you will be able to determine if these reactions will happen or not. But for right now, I just want you to identify the reactions when you see them. So in this first one, sodium reacting with water, you can see that sodium takes the place of one of the hydrogens, and hydrogen gets booted out by itself. Silver nitrate reacting with copper. Copper is going to take the place of the silver, so copper now bonds with the nitrate and boots out the silver by itself. Magnesium is the single element. It's going to take the place of the metal, the aluminum, and so it boots aluminum out by itself, and now it bonds with the phosphate. So you're just having an element in a compound, and you're forming a new element and a compound on their own. So you're just changing the way things partner up or pair up. In a double replacement or a double displacement reaction, you have two compounds, and you form two new compounds where you can think of them just switching partners. the cations are going to switch places or the anions switch places. It's never both of them because obviously you would form the exact same compound on the other side. But one or the other is just going to switch places. We generally see this with ionic compounds in aqueous solutions, so things are dissolved. And when we go through predicting products, you're going to learn how to tell if these will go or not. And they may be written as complete ionic or net ionic equations. When we get into the net ionic equations, essential question for this unit, you're going to learn how to write the net ionic equations for a double displacement reaction. So what's cool is there's different types of double replacement reactions. There's a precipitate reaction where you form something that's a solid that won't dissolve. So that solid precipitates out. So you have sodium bonded to sulfur here, which is aqueous, cadmium bonded to nitrate, which is aqueous, and the cadmium and the nitrate split apart from each other, and the sodium and the sulfur split apart from each other, and now the cadmium bonds to the sulfur. So you form that new compound, and that happens to be insoluble in water, and you also form Na bonding with NO3, which is still soluble, so it would stay aqueous. So the way to determine if these happen or not, you're going to have to use this little chart here called a solubility chart. So something else that you're going to learn how to use. Another type of a double replacement reaction is where you might get the production of a gas. So sodium cyanide and sulfuric acid reacting together, and you can see that cyanide was bonded to sodium on this side, but now cyanide is bonded to hydrogen. And the sulfate was bonded to hydrogen, and now the sulfate is bonded to sodium. So they just switched partners. And then you can have an acid-base reaction where you have like calcium hydroxide bonded to hydrochloric acid, and they just, again, switch partners. The calcium is bonded to the hydroxide, and then it switches to being bonded to the chlorine, and then you're left with HOH, which is water, that form. So different types of, or there's 3 different types of double replacement reactions that we'll go through. So the last type of reaction type to go through is combustion reactions. You're going to see some sort of a hydrocarbon, meaning it can have any amount of carbons to hydrogens. That's why we have X and Y there, because it's just in any hydrocarbon is going to be in any of those, any ratio possible. Plus oxygen. Whenever you burn anything, you need oxygen. It's going to react to form carbon dioxide and water. So this is kind of how you will see all of these set up. You will always see carbon dioxide and water on the product side. You will always see oxygen on the reactant side, and you will always see a hydrocarbon. So it's always a hydrocarbon plus oxygen gives you carbon dioxide and water. So as the hydrocarbon compounds, which contain carbon and hydrogen and sometimes oxygen, but as they react with oxygen, they will burn, and they'll often give off heat or light. These are always going to be molecular because the hydrocarbon is molecular. Almost always exothermic, meaning they're going to give off heat. If the supply of oxygen happens to be insufficient, though, so like if you don't have enough oxygen to keep burning all of that, the combustion will be incomplete, and it may form, instead of forming carbon dioxide and water, you'll form carbon and carbon monoxide. So you'll get this like soot stuff that'll show up. That'll be the carbon and then carbon monoxide. If you are burning hydrocarbons for fuel in your house, like if you have a gas heater, you want to make sure that it's going through complete combustion. If it's going through incomplete combustion, you could be making this soot stuff in your furnace, as well as carbon monoxide, which is why detectors are so important in your house. So some examples: methane plus oxygen gas gives you carbon dioxide and water, or C10H8 plus oxygen gas gives you CO2 and water. And then the last one, we have the CH3OH, so it's going to have some oxygen in it, plus more oxygen when it's burning, gives you carbon dioxide and water. And they're showing heat as a product on this reaction side, and that's okay. Just putting that heat is being produced. Heat's being made. But you can see that these are all hydrocarbons reacting with oxygen to produce carbon dioxide and water. So that's the end of identifying reaction types.